Hello everyone, let's analyze. So recall the Lagrange mean value theorem from a couple lectures ago, which we just called the mean value theorem. But we'll say today the Lagrange mean value theorem to distinguish between this new mean value theorem we're going to look at, the Cauchy mean value theorem. We can look at the Cauchy mean value theorem as a generalization of the mean value theorem of Lagrange. At first glance, of course, it doesn't look alike, but let me give you the theorem and hopefully convince you that the Lagrange mean value theorem is a straightforward result of the Cauchy mean value theorem. Suppose f and g are continuous on the closed interval a to b and differentiable on the interior. Then there is a c in the interior for which the rise of f through a to b times the slope of g somewhere in the interior equals the rise of g on the interval a to b times the slope of f somewhere in the interior. Now, again, that may not look very much like the mean value theorem from before, but if g were the identity function, that is g of x equals x, then Cauchy reduces to the mean value theorem we've seen before. So let's prove the result. We're actually going to prove this generalization of Lagrange's mean value theorem by using Lagrange's mean value theorem. So suppose h of t is the change in f on the interval, that is f of b minus f of a, times g of t minus the change of g on the interval. In other words, g of b minus g of a times f of t. Now, notice that in this statement of f of t, we essentially have a linear combination of g and f. Okay? In other words, we have a scaling of g plus a scaling of f. Right? F of b, f of a, g of b, g of a, these are all just numbers. G of t is a function, f of t is a function. So because h of t is a scaled sum of g and f, h is continuous and it's also differentiable. Because it's continuous and differentiable, we can actually apply the Lagrange mean value theorem, in other words, the mean value theorem we're used to say that there's some value in the interior for which the slope of h, in other words, the derivative of h at c, equals the secant slope of h through a to b. Remember, the mean value theorem of Lagrange essentially says tangent slope of somewhere in the interior equals secant slope. By the way, if we plug in a to the expression h of t, in other words, compute h of a, and compute h of b, we get the same number. Specifically, you get f of b times g of a minus g of b times f of a. H of a and h of b are the same. Now, if h of a and h of b are the same, then the numerator in my secant slope expression here is 0, meaning h prime of c is equal to 0 for some value c in the interior. Now, because h of t is just a scaled sum of g and f, I know what the derivative is of h of t, and I can plug in c. Right? Now, I don't know where c is, I just know that it's in the interior, and I know the derivative is 0 there. Therefore, 0, which equals h prime of c, equals, right, the change of f over the interval times g prime of c minus the change of g over the interval times f prime of c, which essentially proves our result, that the change of f times the slope of g in the interior equals the change of g times the slope of f at that same point in the interior. And we've proven our result. Now, the mean value theorem that the secant slope equals the tangent slope somewhere in the interior is fairly intuitive. Just like if you were able to drive 100 miles away in an hour, at some point you were going 100 miles per hour, right? Those are essentially the same statements, and we understand that intuitively. So, however, this generalization of the mean value theorem turns out to be useful. Specifically, it'll be useful to prove L'Hopital's theorem, which is useful for computing limits of ratios when if you just apply the limit in the numerator and denominator, you get 0 over 0. Rather than banging your head into the wall, we can just take the derivative of the numerator and denominator separately and take the limit of that. Before we get to the proof of L'Hopital's theorem, let me remind you of one of our very important results. That if f has a limit at x naught, and xn is a sequence converging to x naught, but never equal to x naught, then the limit of the sequence f of xn equals L, and it's actually an if and only if statement. So this result and our brand spanking new Cauchy mean value theorem will essentially be our primary tools for constructing a rigorous proof of L'Hopital's rule. So first, let's go over the hypothesis of L'Hopital's rule. F and G need to be continuous on a closed interval. Both need to be differentiable on the interior. G prime has to always be non-zero. Meaning what? Well, meaning G prime is 1 to 1. Meaning G is 1 to 1. Now F and G at some x naught is 0. F prime and G prime has a limit at x naught. Now that's an assumption, right? We're assuming that that's true. So if all these things are true, then the ratio f of x over g of x has a limit at x naught as well. And the limit as x approaches x naught of f over g equals the limit as x approaches x naught of f prime over g prime, which is the L'Hopital rule as we understand it. So we're going to transform our world of continuous function to a world of sequences. So because a limit at x naught exists, x naught is an accumulation point, meaning we can craft a sequence xn where xn is never equal to x naught, but xn converges to x naught. What we would like to show is that f of xn divided by g of xn converges, because if we can do that, then we've proven that f of x over g of x converges as x approaches x naught, which is our goal. That's the result we want to prove, and then also, of course, give a value for it. So I have my sequence xn converging to x naught, and well, in between xn and x naught is a Cn guaranteed by the Cauchy mean value theorem, the mean value theorem we talked about today. So what happens at that Cn? Well, the change in f from xn to x naught times the slope of g at Cn equals the change in g from x naught to xn times the slope of f at Cn. Right, this is essentially saying that because xn and x naught are not equal, for every xn there's a point in between, Cn, and we can apply the statement of the general Cauchy mean value theorem to that. Now, notice that g of xn and g of x naught has a non-zero difference because they're not equal. We know they're not equal because g is 1 to 1. We know g is 1 to 1 because its derivative is non-zero, meaning g never made a U-turn. However, in the hypothesis, f of x naught here, here, here are 0. Meaning, if I take this statement at 2, divide both sides by this change in g, and divide both sides by the slope of g at Cn, I get this statement here, but I can get rid of the f of x naught and g of x naught to get this ratio, because f of x naught and g of x naught are 0. So, that's pretty interesting. The ratio f of xn over g of xn for every value of n is exactly equal to f prime of Cn divided by g prime of Cn, where Cn is some value sandwiched between xn and x naught. Now, because xn converges to x naught, and Cn is sandwiched between xn and x naught, then Cn also converges to x naught. We also know that f prime of xn over g prime of xn is a convergent sequence, because we assumed that f prime of x divided by g prime of x has a limit at x naught, and xn converges to x naught. Let's call that limit L. And because Cn also converges to x naught, f prime of Cn over g prime of Cn also converges to L. But remember, f prime of Cn over g prime of Cn is exactly equal to f of xn divided by g of xn. That's how we're able to go to a ratio of derivatives to the ratio of the original functions f and g. Because these two sequences are exactly the same. And if this one converges to L, then this one converges to L. And because L is equal to the limit as x approaches x naught of f prime over g prime, we get the limit as x approaches x naught of f over g is also L. And we've proven our result. We've proven L'Hopital's theorem. Now, a quick word of warning about the correct pronunciation of L'Hopital's rule. It is pronounced, well, the way I've been pronouncing it the entire lecture. L'Hopital's rule. It's not pronounced hospital. You will sound silly if you call it La Hospital rule. Almost as silly as if you ordered tortillas. Now, some books actually spell it with an S. Some take the modern French approach, which is to get rid of the S. Either way, it's still pronounced L'Hopital. In fact, it helps if you can affect an obnoxious fake French accent, L'Hopital. Though, of course, if you are French, well, it's crucial that every ounce of your Frenchness oozes out of your pronunciation, and you'll be the envy of your class. Now, what about the rest of his name, you ask? Oh, you didn't ask? Well, I'm going to tell you anyway. His name is huge. His name is Guillaume François Antoine Marquis de l'Hôpital, Marquis de Saint-Mont, Comte de Entremont et Seigneur de Auch-la-Choix. With a name and hairstyle like that, I mean, it was either rock star or mathematician. Well, since he preceded the invention of rock and roll by a few centuries, well, math it was. L'Hôpital was actually tutored by the very famous mathematician Johann Bernoulli. He had money if he can hire Bernoulli as a tutor. Many of the ideas he learned from Bernoulli appear in his book, Analysis de Infinité Petite pour l'intelligence de l'incurve, which is the analysis of infinitesimal pieces for understanding curved lines, is what I think that title means. It's published in 1696 when I was very young. It's the very first textbook ever written on differential calculus. So, thank you. Party on, Marquis. And that's it for this semester.